Hello and welcome everybody. In this video, we're going to take a look at the notes for AP Physics 1 unit titled Circular Motion and Gravitation. Please remember to pause and rewind the video as you need to. I will pause during certain test your understandings so that we can, and I would encourage you to pause the video as well so that you give yourself a chance to try those. Something different about this video, I will be going over all the examples. Okay, none will be done in class. So please make sure you pause and rewind the video as needed. Let's begin. Section 4.1, the qualitative velocity change method for circular motion. How is velocity directed when an object travels along a curved path? When an object travels along a curved path, the velocity is directed tangent to the path. How can an object have constant speed and yet be accelerating? Well, up until now, we've looked at acceleration model as being some object that is speeding up or slowing down. Now we see that to accelerate, you actually have to change your velocity, which means it could involve increasing or decreasing your velocity in terms of your speed, but it could also involve changing the direction. So how does an object have constant speed and yet accelerate? Well, the object must be curving and changing the direction. The direction must be constantly changing. I will do this test your understanding with you so that you have an idea of how to approach this model, and then I want you to give the second one a try by pausing the video. Let's take a look at this test your understanding. The diagram below shows an object in projectile motion. The position of the object is shown at regular intervals of time. Each position has an arrow representing the object's velocity for that instant. For each pair of vectors, draw both the vectors on the dot exactly to scale, and then draw the vector delta v between them. Okay, so something to note about delta v. Delta v, this vector delta v, is it's the change in velocity. It's v2 minus v1, or it's the second velocity minus the first velocity. Or you could look at it as the, change the color here. You could look at it as v2 plus a negative v1, right? It's another way to look at it. So I'm going to show you kind of a longer way to do this, and then I'm going to show you a nice little shortcut. And go ahead and try to apply the shortcut when you attempt this on your own. Okay, how do we draw these to scale? Well, you can see the velocity vectors are mapped out here in this diagram. So let's all begin. I'm going to begin by drawing in blue the original vectors, okay? So we're talking about v naught and v1. Those would be those two vectors right there. So you can see v naught is directed 2 units up, 2 units over. So I'm going to draw an arrow that is 2 units up, 2 units over. That would be v naught. You all can see that v1 is directed 1 unit up, 2 units over. I'm going to draw them both tail to tail, coming from the dot just like that. And there would be v1. Now, one of the things that we learned in one of our last sessions was the parallelogram method of vector addition, in which case when the two tails are together, we create a parallelogram, and then from where the two tails meet to the opposite side of the parallelogram exists the resultant vector. In this case, the resultant vector is going to be this thing called delta v. Now, since acceleration is the change in velocity over time, that means whichever way delta v is pointing, that's the way acceleration is pointing. Let's take a look. Now, in a different color, I'm going to, in order to get this right here, I need to go basically v1, the second velocity, plus a negative v naught. Now, v naught points 2 units up and 2 units over. Negative v naught would point exactly in the opposite direction, where this vector is pointing. This would be negative v naught. So now what we can do is we can complete the parallelogram, which would be this side is parallel to that side, and then this gray side is parallel to that side. Okay, so we've completed our parallelogram. And in black, I'll go ahead and draw from where the two tails are meeting to the opposite end. There's our delta V. Okay. Now this is kind of the long way to do it. A much shorter way and an easier way, I think, would be you draw your two vectors, both tails coming from the object, and what you do is you draw an arrow from the tip of one vector to the tip of the other, just like this. From the tip of one vector to the tip of the other vector. And you can see that that arrow is exactly the same length, which means same magnitude, and the same direction as the arrow that was drawn from the dot. This is a much faster way to come up with this result. Okay, so what I want you all to do is take a moment, pause the video, go ahead and draw V1 and V2, B3 and B4, V2 and B3, excuse me, B3 and B4. And then after you do so, draw delta V. Go ahead and give this a try. Pause your video and we'll resume in a few moments. Okay, well, we already saw V1 is going 2 units over, 1 unit up. There's V1. You can see V2 is going directly horizontal. Just like that. I'm going to draw all the vectors first, and then we'll talk about the direction of delta V between those vectors. So this would be V2. Okay, again, V2 goes directly to the right, 2 units. V3 is going 2 units over, 1 unit down. That would be like this. There's V3. And then V3 is going 2 units over, 1 unit down. And V4 is going 2 units over, 2 units down. Just like that. Okay, so your original vector should have looked just like this. Now, to draw delta V, you're simply drawing it from the tip of the first vector to the tip of the second one. At least that was the shortcut that was shown to you. There's delta V. There's delta V. And there's delta V. In what direction is the acceleration, which by the way points in the same direction as delta V, of every object in projectile motion? Remember that direction of acceleration, again, is in the same direction as delta V. Well, if you notice, delta V is always 1 unit in magnitude pointed directly down. And that should make sense because the only thing that causes a projectile to accelerate is the force of gravity. It's the direction of the curve is up and down, not left and right. Test your understanding. The diagram below shows an object in uniform circular motion. Uniform circular motion means constant speed in a circle with constant radius. The position of the object is shown at regular time intervals. Each position has an arrow representing the object's velocity at that instant. For each pair of vectors, draw both the vectors on the dot exactly to scale. Draw the vector delta V between them. Then draw the acceleration vector at the draw an acceleration vector at the letter point on the diagram to the right. Okay, so we have letter points here, A, B, C, D, and we need to draw the acceleration for them, okay? So let's first go ahead and pause the video. Go ahead and draw the vectors, the vector pairs. Draw delta V And then let's figure out where the acceleration points. Go ahead and give it a try. Okay, let's see what you came up with. Again, let's first draw the vectors. V naught, as you can see in the video, or we're looking in the picture here, we're going to plot V naught and V1. Well, V naught is going 2 units over 4 units up. V1 is going 4 units over 2 units up. So let's go 4 and 2 and 4 would be like this. There's V naught. And we know that V1 is going 4 over 2 up, just like that. Again, let's draw the vectors first, then we'll deal with delta V. Okay, we know V1 is going 4 units over 2 units up. And you can see that V2, well, it looks like it's 4 units over to the right, but it's actually a little longer. Notice the arrow tip goes almost 4.5 units. So that's the way I'm going to draw it. About right there. Clean this one up a little bit better. There we go. Okay, so V2 again is going a little more than 4 units over to the right. And V3 is going 4 units over, 2 units down. Just like that. Okay, and then lastly, V3 and V4. So V3 is going 4 units over, 2 units down. There's V3. And V4, you can see, is going 2 units over, 4 units down. So that would look something like this. Okay, drawing delta V just simply means connect the tips. There's delta V for point A. And let's go ahead and draw on the vector. Point A, you can see it's going directly 2 units over, 2 units, it's going right in that direction right here. Exactly in that direction. I'm going to label this A for acceleration. In point B, well, it would look something like this. There's delta V. Point B, it's going almost a half a unit over and 2 units down. Like about there. There's A. But I'm supposed to be drawing this on point B, so let me fix that. There we go. That's better. At point C, you can see kind of looks as though it's going a half a unit to the left and maybe 2 down. That would be at point C. And then lastly, at point D, this one's an easy one. You're going 2 units to the left, 2 units down. Just going directly this way. Okay. In what direction is the acceleration of every object in uniform circular motion? Well, look at what they all have in common. The acceleration points toward the center of the circle. Section 4.2. Test your understanding. All of the objects move in a circle at a constant speed. Draw and label only the force that each example asks for. Pause the video and try and figure out which force needs to be drawn, and then draw that force. Okay, let's see what you came up with. Well, the force here would be a gravity force, so we can draw an arrow from the Earth to the sun, labeled F sub g. A ball on a string is whirled in a circle as seen from above. So this is a horizontal circle. Draw the tension. Tension would be pulling towards the middle of that circle. Ball rolls around a vertical track. Draw the normal force. Well, the normal force is drawn from the surface onto the object in a perpendicular fashion. So the normal force would be pointing just like this. And a car goes around a curve as seen from above. Draw the frictional force. Well, it's the frictional force from each tire that point toward the center of the circle, allowing the car to actually navigate the circle. An electron orbits a proton in a hydrogen atom. Draw the electric force. Well, positive attracts the negative, very similar to a gravitational attraction. We're going to label this one, though, in case you didn't know how to label it. An electric force, we can label that F sub E. Just like a gravitational force is F sub G, an electric force is F sub E. Biker goes over the top of a hill. Draw the weight and normal force. Well, weight goes directly down. But is it down? Not necessarily. It's towards the center of the circle. We'll come back to that one in a minute. And then you have the normal force applied from the surface straight upward. But is it exactly upward? Not necessarily. We're looking into the circle and out of the circle. Come back to that in a moment. A rock moves in a horizontal circle. Draw weight and tension. Okay, well, tension will be going away from the rock up the string, like this. There's tension. Weight would be directed straight down. Since tension is at an angle, we would need components. Now, if this were an actual free body diagram, you would not draw components on a free body diagram, but this is not a free body diagram. I'm just asking you, again, for the forces involved. So tension's at an angle, so we need component of tension going over and a component of tension going up. Since this is the adjacent side of that triangle, this would be tension cosine theta. Since this is the opposite side of the triangle, this would be tension sine theta. A ball rolls along a dotted path on the inside of a cone. Draw the weight and normal force. Well, the weight, of course, would go straight down. The normal force would go perpendicular, just like that. Now, this is very similar to a banked curve example, which we'll get to at a later time. But this is one of those times where we want a component of the normal force, not necessarily the weight like we would at an inclined plane. The reason we want a component for the normal force is because we want a force that is going in this direction here. See, the acceleration always goes towards the center of the circle, and we want a force that's going to go that way too. So we want components for n. We're going to have components that go into the center and straight up opposite the weight. All right, now let's figure out what our, use little similar triangles here, and let's figure out what's going on. Okay. Now, you know that this angle here, and this angle here are exactly the same because those are alternate interior angles. Which means if this whole thing is 90 degrees here, that means this angle here and this angle here are complementary and add to 90 degrees. That makes this angle theta the same as this angle theta up here. So just doing a little bit of work with the angle relationships that exist in similar triangles, we can figure out how these thetas, how these angles appear in different parts of the picture. Well, the vertical part is the adjacent side of the triangle. That would be normal force cosine theta. This vector here is the opposite side. This would be normal force sine theta. When an object moves in uniform circular motion, what is true about the net force? Well, just like Newton's second law, net force, the direction of net force is equal to, or is in the same direction as acceleration. That is no different for center pointing acceleration. So the net force always points in the direction of acceleration, which is towards the center of the circle. Okay, let's write an equation for these various examples. For the second law, now we're going to do a second law equation, but this is how we're going to express it. We're going to write an example for the net force. The net force equals MAC. We'll talk AC stands for centripetal acceleration. Okay, write an expression for Newton's second law for the biker going over the hill. So this example right here. Well, what's the force that causes the bike to go in a circle? Well, that would be the force that's pointing towards the center of the circle. That'd be gravity. So we've got the force of gravity. And just like we had for net force, causing force minus opposing force equals ma. Well, causing forces point and cause the curvature. Opposing forces point away from the curvature. So that makes this a causing force. It makes the normal force an opposing force. So in this example, gravity, force of gravity minus normal force equals MAC would represent this scenario here. Write an expression for Newton's second law for the rock on a string. Okay, now Newton's first law would be to balance the forces of T cosine theta going up and mg, the weight, going down. But that's a first law example, not a second law. The second law would be an example where we're accelerating. We accelerate in the direction of the circular motion, which would be towards the center of the circle. Therefore, in this example here, the net force would be T sine theta is equal to ma, because T sine theta is what causes the curvature. Write an expression for Newton's second law for the ball in a cone. Similarly, n sine theta is pointing to the center of the circle, and thus n sine theta is what is causing the circular curvature and the changing of direction, and therefore the centripetal acceleration. So n sine theta equals MAC. Explain how to construct a Newton's second law equation for an object going in circular motion. Well, basically, forces into a circle minus forces out of a circle because this would be the causing force and this would be the opposing force, equal MAC. Now I'm going to give you a little bit of heads up on something that we're going to come back to. We're going to be rewriting the AC in terms of the tangential velocity around the curved path and the radius of that curvature. Okay, more to come on that. We'll come back and revisit that topic soon enough. Now we can just kind of summarize this as forces in minus forces out equals MAC. That's just sort of a shorthand way of writing it. Remember, forces in cause the acceleration, forces out oppose the acceleration. Section 4.3, radial acceleration and speed. Well, now we talk about the relationships. What type of relationship exists between the acceleration, the centripetal or radial acceleration, and the speed of the object? Well, as it turns out, and we're going to do this and verify this experimentally, the centripetal acceleration is not just proportional to speed, but it's proportional to the square of the speed. Another thing we'll find out is that the centripetal acceleration is inversely proportional to the radius. Okay, so putting that together, AC is directly proportional to the square of the velocity and inversely proportional to the radius. We get an equation that looks like A sub C equals V squared over R with no constant of proportionality needed. Now we come back to this equation here. Remember AC? Well, if we substitute V squared over R in place of AC, well, turns out for centripetal forces, forces in minus forces out equals mv squared over R. This is how we will express it in most cases. Newton's second law for uniform circular motion. All right, let's take a look at this example. Consider a car approaches an intersection to make a turn. The car can either make a left turn or a right turn, as shown in the diagram. Assume that the car approaches, makes the turn, and continues forward without changing speed. The centripetal force is provided by static friction, which is determined by the relationship friction is less than or equal to mu times the normal force. Now, in class, we've usually written it like this. F is less than or equal to mu times normal force. But when we talk about the equal, we're talking about the maximum static friction. So in most cases, we just typically write it as mu is equal to, friction is equal to mu times normal force, where that's the static friction and that's the coefficient of static friction. That's typically the way we would write it in class. Explain why the force of static friction, not kinetic friction, acts on the car even though the car is in motion. Well, static friction is what prevents skidding and sliding. And as you navigate the turn, you don't want to skid. You want to keep going in a circle. So static friction is going to keep you going in a circle and prevent you from skidding. Explain what happens to the value of mv squared over r. What happens if that is greater than mu times normal force? Okay, so something to consider. We'll write this over to the side here. Friction is our net force. So friction is equal to MAC, which means friction is equal to mv squared over r. Now friction, right here, is equal to mu times normal force, and that's equal to mv squared over r. And if you were to take a look at the car from the side view, you'd have the weight mg going down and you'd have the normal force going up, which means the normal force going up balances the weight going down. So I could actually rewrite this as mu times m times g equals mv squared over r. And again, I'm using the equals because I'm using a case of maximum static friction, not any smaller variety of static friction. Notice that cancels. and we have a relationship that says mu times g. Okay, and we could keep it the way it was before, but mu times g is equal to v squared over r. Now, what this means is v squared over r is a constant for every circle if you're to maintain the frictional force in that circle, because mu is a constant and g is a constant. Now, you can rewrite this, and that's going to be helpful to do for certain instances. Solving for v, we have v squared is equal to mu times g times r, and then square root both sides. So we've got an expression for v that basically says the bigger the circle, the faster the speed you can go around it. That makes a lot of sense. So going back to the question, explain what happens to the value of mv squared over r if it's greater than mu sub n. Well, if mv squared over r is greater than mu sub s times the normal force, then there's not going to be enough static friction to hold the car along that curved path, and the car's going to skid. Basically, what does that tell you? Too fast for a given radius, the friction's not going to hold. And we can look at it from this point of view too. If you look at this particular equation here, v squared and the radius have to remain the same. So if I have a large circle, I can go faster in that large circle to maintain the same friction force. Similarly, if I have a very small circle, I have to navigate it much more slowly to keep that same friction force. Which turn, left or right, requires the car to slow down more in order to make the turn safely? Explain your answer using appropriate relationships. Well, we just got done talking about that. A right turn would require a slower speed. If you look, a right turn has a much smaller radius of curvature, whereas this has a much larger radius of curvature. So since the right turn has a smaller radius of curvature, it's going to require a smaller v speed in order to keep the same friction force. Explain what period is. Explain what frequency is. Well, period is the time it takes for one cycle. Frequency is how many cycles are made in that unit of time. We can express this kind of a different way. Period is the variable for period is a capital T, because it is a very specific time measurement. The units for it would be seconds per cycle. Frequency uses a lowercase f, very similar to friction, but it's one of those times where we share the same letter but for a different variable. Now, period, even though it's seconds per cycle, cycle means how many circles are you making, right? How many revolutions are you making? How many turns of a circle are you making? And so that's not really a legitimate unit per se. So the unit for period is really just seconds. The unit for frequency is the inverse of the unit for period. It is how many cycles happen in each second. Now, cycles per second is one particular unit for frequency, or the more common one would be hertz, which is abbreviated Hz. More to come on period and frequency, as we'll address them a little bit here in uniform circular motion, but much more developed in our unit next semester on simple harmonic motion. Test your understanding. Circle to indicate whether each quantity is frequency, period, or other. Please pause the video now and test yourself. Go ahead and begin. Okay, let's see how you did. Number 1, the second hand of a clock makes 60 seconds to travel around the clock. Well, focus on the unit, right? So 60 seconds, well, that would be period. The hour hand of a clock travels around the clock 2 times every day. Times would be a cycle. Therefore, this is referring to frequency. 2 times a day would be the frequency. Number 3, each second as it orbits, the Earth travels 18 miles. Well, if you're talking about time to travel a certain distance, that's neither frequency nor period. That would be speed. Number 4, the Earth rotates 30 times each month. That refers to cycles, that refers to frequency. The Earth takes 365 days, that's a period of time, to complete one cycle. That would be the period. A trucker averages 600 miles every day. So distance given a unit of time, of course, is a speed concept. What is the new equation relating speed, period, and radius in uniform circular motion? What basic equation does this new equation derive from? Okay, so let's start with the second part of that question. A very basic equation that we started with in the very beginning of the year was the idea that speed is equal to distance over time. Now, if we're talking about around a circle, the distance would be the circumference of the circle, and the time around the circle would be the period. So if we change this up, the circumference, we would replace d with 2 times pi times the radius, because that's how you calculate circumference, divided by t. V equals 2 pi r divided by t. What is an equation relating centripetal acceleration, period, and radius? All right, well, there's a couple of them really, but here's one that we can work with. Start off with the idea that a sub c is equal to v squared divided by r. Okay, now I'm going to go ahead and swap those two right there. And we get r is equal to v squared over a sub c. Now I'm going to take this value for r right here. I'm going to replace it for r right there. So v is equal to 2 pi over t times my value for r, which is v squared over a sub c. So now we have a new equation. V equals 2 pi v squared over t times a. Now you have v on one side, v squared on the other. They're the same v, so that effectively cancels. And that leaves you with what cancels on the left side, that leaves you with the number 1. So what I could do is I can multiply both sides by a sub c, like that. And we end up with a sub c is equal to 2 pi times the speed over the period. So we've got velocity is equal to 2 pi times the radius over the period. The acceleration is 2 pi times the speed over the period. Very similar equations. Test your understanding. A car takes 3 seconds to make a left turn without changing speed at the intersection of 2 perpendicular streets. What is the period of the car's circular motion? Now, pause the video, see if you can figure out what the period of the car is going to be making this left turn. The hint I will give you all is the period is the time to complete one full cycle, or in this case, one full circle. Pause the video and give it a try. Okay. To make a left turn, and it takes 3 seconds to make a left turn, you are only going a quarter of a circle. That means another 3 seconds, another 3 seconds, and another 3 seconds means that the actual period is going to be 12 seconds. If it were to navigate a full circle. And the period talks about the time it takes to complete one full cycle. Example. An accelerometer is placed in a car. Now, in many cases, actually, accelerometers are a part of cell phones. It's what makes your cell phone screen turn from one view to another view by rotating it. The accelerometer in the phone helps that process to happen. And there are many acceleration apps that can be downloaded to actually measure what this example is describing. But anyway, let's continue to read. The accelerometer measures the acceleration of the car in the car's reference frame along the two axes X and Y shown. So the car's reference frame means the car relative to the ground, not a person relative to the inside of the car. There's a difference. Person relative to the inside of the car appears to be at rest, but the car relative to the ground is moving. The car is initially traveling along a straight path. The car then makes a 90-degree turn without changing speed. The acceleration along the x-axis is shown in the graph. The acceleration measured along the y-axis is not shown. So the acceleration that's shown is only the x-direction acceleration. Now, let's take a look at the picture. We can see that the x-direction acceleration would point to the right or left. The y-acceleration points forward to the front of the car or backward. Now, you can see pretty clearly that from 2 seconds to 5 seconds, we have 3 seconds of acceleration in the x direction. How do we know? Because we were told the graph only measures acceleration along the x-axis and not along the y-axis. So we know that this is 3 seconds of acceleration in the x direction. Now, since all of these values of acceleration here are above 0, they're positive. So one thing to note, positive y acceleration means that we are speeding up. Because positive y would be going forward. Negative y acceleration would be slowing down. Since x, positive and negative x point to the left and right, that would be centripetal acceleration causing the car to curve or turn in part of a circle. Question says, what would the graph of acceleration along the y-axis look like? So we're given the graph of acceleration along the x-axis as a function of time, but what would the graph of acceleration along the y-axis look like? What evidence from the question would indicate this? Well, again, positive y would be speeding up, negative y would be slowing down, and we were told that the car makes the turn without changing speed. So that means that the car did neither of these things because it turned the corner at a constant speed. And a little bit of a typo here on this sentence. And so to kind of finish off this question, since it's not speeding up nor slowing down, it means the acceleration would be 0. The acceleration graph would be constant at 0. Does the car make a left turn or right turn? What evidence suggests this? Well, as we saw earlier, that is all acceleration in the positive x direction. Positive x goes to the right, therefore, acceleration is positive, and therefore the car is turning to the right. Use the graph to determine both the speed of the car and the radius of the turn. Each step of mathematical work must be accompanied by words explaining what is done from each step to be taken. Okay, well, A sub c is equal to 6 meters per second squared. Now, how am I coming up with this number? If you go to the graph, you can see that the value of the acceleration is fairly constant, right about 6. So we can say the average acceleration for this turn is 6 meters per second squared. Okay, and this is taken from the horizontal part of the graph. Now, the period is 12 seconds. How are we coming up with that? Well, the time it takes to curve goes from 2 to 5 seconds. The time for the curve for curving is 3 seconds. Therefore, the period would be completing the full circle if indeed it did go a full circle, and that would take 12 seconds to complete a full circle for that particular curve. So the period is 12 seconds. We can use the equation a sub c equals 2 pi r over, 2 pi v over t. And we can use the equation a sub c equals v squared over r. So v squared over a will help you find the radius. And to find v, we would need to multiply by t. So v is equal to t times a sub c over 2 pi. So 12 seconds times 6 meters per second squared over 2 pi, which is approximately 6.28. And we'll put that in our calculator. We get approximately 11.5 meters per second squared. Meters per second, rather. And that makes this a really easy calculation of 11.5 squared over 6. And we get approximately a 22 meter radius of circular curve. Circular motions. Now, this part's not in the book, so again, please make sure that you pause or rewind the video as you need to. When an object accelerates, the object is either speeding up, slowing down, or changing direction. Changing direction is kind of what we're referring to more in this unit. Now, there are two types of acceleration, both measured in meters per second squared. Tangential acceleration either refers to speeding up or slowing down. That's because tangential acceleration goes in the direction of velocity, right? Or against direction of velocity if you're slowing down. And velocity goes tangent to the curve. Centripetal, center pointing, is where the word is derived, meaning the acceleration points to the center. An object that has centripetal acceleration is changing direction. Specifically, the object is curving in a circle. Curving in a circle or part of a circle, for that matter. Okay, curved motions. Now, this is normally meant to be a cut and paste activity, but this is something we can just sort of draw to illustrate these differences. So go ahead and copy this along with me. The first row refers to no centripetal acceleration. Well, ladies and gentlemen, that would just be linear motion, as we've studied it up until now. The second row is involving centripetal acceleration, so this would be curving in a circle, or again, part of a circle. So, if you're moving at a constant speed, what would the motion diagrams look like for velocity and acceleration? Well, velocity, draw a dot, label the V, there's velocity. And the thing about constant speed is velocity at a constant speed would be the same, the dots would be equally spaced apart, and each arrow representing the velocity would be at the same length or the same magnitude. And notice I don't have an acceleration vector in there because constant speed means you're not accelerating. Now, speeding up, how do we illustrate that? Well, start with a dot where we're kind of talking about maybe V naught is 0, perhaps. And then maybe a dot a little while later with a short arrow. And then a dot farther away with a longer arrow. And then a dot farther away with a much longer arrow. And so as the velocity is increasing, right, the acceleration would point in that direction. Acceleration goes in the same direction as an object speeding up. Now, slowing down would just be the exact opposite. Longer arrows, shorter arrows, until maybe you end up with nothing. When an object is slowing down, the acceleration opposes the motion, goes the opposite way. Now, if we're curving in a circle at a constant speed, like in the first column, then what we'd have is we'd have some arrows, all the same length, going around the edge of the circle, fairly equally spaced apart. The difference is you have no tangential acceleration because you're going at a constant speed, you're not speeding up or slowing down, but you do have centripetal acceleration. All of which would be pointing to the center of the circle. So again, velocity is tangent to the path that you take, and acceleration and net force point towards the center of the circle. Now, what if we're speeding up as we're going around the edge of the circle? Well, we'd have arrows that were getting longer, like that. It would be your velocity vectors. Your speed is increasing. You'd still have centripetal acceleration. Still points to the center. But the overall acceleration would be a little bit different because now you'd have a tangential acceleration, which I'm going to call A sub t. And you could see A sub t is pointing in the same direction as velocity because it is the tangential acceleration that involves an object speeding up or slowing down as it's navigating the curve. Okay, so now if we're slowing down, exactly the opposite. Longer arrows. Like that. Velocity vectors are getting shorter. We're slowing down. We still have centripetal acceleration pointing towards the center. This time, the tangential acceleration points away or against the velocity. Answer the following questions using the word right, acute, obtuse. What is the relationship between velocity and acceleration when the object is speeding up? We're talking about the overall acceleration. Well, we'll do this in gray. Answer the following questions. Use words like right, acute, and obtuse, or components, etc. What is the relationship between velocity and acceleration when an object is speeding up? And when we're talking about acceleration, we're talking about the overall acceleration. That means the combination of any centripetal or tangential acceleration. Well, when an object's speeding up, I'll show this to you in gray. You can see how the angle between the gray arrow right here and velocity, the blue arrow, is an angle less than 90 degrees, meaning F is acute with V. And we're saying F, this is the relationship between velocity and acceleration, so A is acute with V. What is the relationship between velocity and acceleration when an object is slowing down? Well, again, the overall acceleration is now away. And the angle between the blue velocity vector and the gray vector is now a larger obtuse angle, greater than 90 degrees. And so A is obtuse with V, okay? So when we're speeding up, the angle between acceleration and velocity will be smaller than 90, acute angle. If it's slowing down, it'll be an obtuse angle. And if it accelerates, but it does not speed up or slow down, that means we're talking about centripetal acceleration, meaning we're talking about uniform circular motion. Again, uniform circular motion means that we're moving in a circle at the same speed, but we're accelerating because we're changing direction. In this case, velocity is perpendicular to acceleration. Velocity goes tangent to the curve, and acceleration goes perpendicular to that, pointing to the center of the circle. Why is there no centrifugal force? Okay, so if you're sitting in a car and the car all of a sudden makes a sudden left turn, you feel as though you're being forced into the car door, meaning something feels like you're being forced to the right. Are you actually being forced to the right? Let's examine this example. Consider a car that makes a very fast left turn as shown below. In the back seat are a bowling ball and a golf ball. Assume the car does not roll over. Draw the path that the left and right mirror take during the turn. I'll do that in black. So here's the left mirror making the turn, and here's the right mirror making the turn. Draw the path that the bowling ball and the golf ball take during the turn. Assume the back seat is frictionless. Well, if the back seat is frictionless, there is nothing to prevent the bowling ball and the golf ball from doing exactly what they want to do. And when the car is going straight, the balls in the back seat want to move in a straight line. And that's exactly what they do. The golf ball and the bowling ball are back here. And the bowling ball wants to go straight. And the golf ball wants to go straight. Now, when the car is to this point right here, making that turn, it appears as though the balls are being forced to the right, towards the right rear door. Just like it appears as though a person in the passenger seat is being forced to the right into the door during an abrupt left turn. The reality is far from different. There is no force that's pushing anything to the outside of the circle. Are balls being forced to the outside of the circle? No, they're not. Basically, this is due to the inertia of the objects. The objects wish to keep going in a straight line according to Newton's first law. And if they don't, it's because some net force is changing direction and accelerating. Well, what happens? They keep going in a straight line until the car door applies a force, in this case a normal force, to force the golf ball and the bowling ball to curve in a circle along with the car. Think about it this way. If there were no doors on either side of the car, the balls would just keep going in a straight line directly out of the vehicle, like this. And so it would appear that the balls are being thrown out of the car to the right-hand side, but really what's happening is the car is just simply moving left relative to the balls, which are going straight. Section 4.5, Law of Universal Gravitation. The law of universal gravitation basically states that every object in the universe attracts, hence gravity, every other object. All objects essentially attract each other in some way, shape, or form. So we state it like this. The equation for Newton's law of gravity is that F sub g, that's the gravitational force, is equal to big G times M1 times M2 over R squared. Let's break down what these variables are so that you can get a better understanding of these. F sub g is the gravitational force. The gravitational force is in newtons, and it's going to be attractive. M1 and M2 are two masses, mass 1 and mass 2 respectively, both in kilograms. And R is the distance between the center of these masses. G, big G, is what is referred to as the gravitational constant. And its value is a very small number of 6.67 times 10 to the negative 11. You do not need to memorize this number. Even on the AP exam, it's provided for you in a table of information. Okay, so if we were to look at a picture here, you have two masses, let's say M1 and M2. They're separated, their centers are separated by some distance r. Then there's an attractive force, right, going on between those two objects, and that attractive force, of course, would be gravity. So we're looking at gravity from a different point of view. So far, we've looked at gravity as the weight of an object that pulls an object down to the center of the Earth, but that is when we apply gravity at the center of, or at the surface of the Earth. When we talk about gravity at the surface of the Earth or the surface of some planet, then gravity is equal to m times g, where g was 9.8 meters per second squared, and we round that up to 10 all the time. But if we're talking about universal gravitation anywhere away from the center of the Earth or somewhere in space or even just between any two objects anywhere, it doesn't matter, then we use this equation to reference the gravitational attraction between them. Pause the video and try to put the information into this equation and see how well you're able to make the calculation. What is the force of gravity, in other words, F sub g, if Earth has a mass of 5.98 times 10 to the 24 kilograms, that would be M1, and the Moon has a mass of 7.35 times 10 to the 22 kilograms, that would be M2, and the distance between them is 3.84 times 10 to the 8, that would be R, and then you square that. Pause the video right now and try and see if you can make this calculation happen correctly. Okay, let's see how you did. First thing, we got to make sure we're putting in the numbers correctly. So F sub g is equal to big G times the mass of Earth times the mass of the Moon. So instead of using M1 and M2, I'll give them subscripts to remind me what I'm dealing with, divided by r squared, this distance between them. So I'm going to write a big set of parentheses for this part right here, because this is literally one number times one number times one number. Three numbers multiplied times each other. So that would be G. G was the gravity constant, 6.67 times 10 to the negative 11. I'm going to multiply that times the mass of Earth, which, if you remember, was 5.98 times 10 to the 24. And that's going to be multiplied times the mass of the Moon, which is 7.35 times 10 to the 22 kilograms. All that's going to be divided by R, which is 3.84 times 10 to the 8, and then we need to square that. So we're going to square that part right there. Now, if you're not comfortable putting all of this in your calculator at once, meaning you're not comfortable using parentheses, then I urge you to try it with this approach. Multiply these three numbers, write that number down. Square that number, write that number down. And then go ahead and divide the two numbers. That would be the safer way to approach this calculation. But if you do, feel comfortable using the parenthesis functions in your calculator, then putting this in correctly, you should have gotten about 1.99 times 10 to the 20 newtons. On which object is this force applied? The Earth, the Moon? Well, actually, ladies and gentlemen, it's both. It's both, because Earth is applying a force on the moon is applying an equal and opposite force back on Earth. Which object has the greater acceleration? Well, the moon does, because the moon experiences less mass. So this is Newton's second law. Net force equals ma. If the net force is the same between the Earth and the moon, the one with the smaller mass is going to experience the greater acceleration. Okay. In this next section, we're going to deal with Newton's law of universal gravitation, but we're going to use a proportional reasoning approach. I'm going to do the first three with you, and then I'd like you to try pausing the video and see if you're able to figure out how the force has changed when certain variables are changed. Here's how it works. When you see phrases like a certain variable has doubled or cut in third or tripled or you name it, when something has happened to a variable that's written in relative terms, then we can use a proportional reasoning approach as opposed to the actual equation for universal gravitation. And here's the proportional reasoning approach. It's the same equation. Instead of an equal sign, we write the proportionality symbol that looks like alpha, looks like the little fishy. And it's everything except for the g constant. So it's m1 times m2 divided by r squared. So we basically use the gravity equation. We just don't need the gravitational constant because it's a constant. It doesn't change. All we are worried about are the variables that can change. Now here's the way it works. If a value does not change, you're going to replace the variable with the number 1. If the variable does change, you're going to state a number by how much it changed. So if something doubles, you would replace that with a number 2. If something triples, you'd replace it with the number 3, and so on. So let's try this out. Again, I'll do the first 3 with you. Then I'd like you to pause the video and try and see if you can do the last 3 yourself. I see right here mass X is doubled. So I see the word doubled. Automatically, it's telling you, that's kind of giving me a little clue. Oh, I should probably try some proportional reasoning to try and solve this problem. So F is proportional. F prime, that's what we're looking for, our new gravitational force, F prime, is proportional to mx times my all over r squared. Now, mx has doubled. So in place of mx, I'm going to put parenthesis times parenthesis over parenthesis squared. So in place of mx, I'm going to put the number 2 because doubled means 2. Now, we were only told that mass x doubled. That means mass y did not change. So I'm going to keep that as a number 1. Number 1 here indicates something didn't change. And the distance between the masses did not change either. Therefore, that is also a number 1. Okay, filling out the calculation, we have 2 times 1 is 2 over 1 squared is 1, and we get 2. What does this mean? It means the new force, F prime, is 2 times the original force. What does this mean? The force has doubled. The new force has doubled. So by doubling the mass, we have the force between them has doubled. You can leave your answer like this, but know how to translate it into words as well. Second one, mass y is doubled. Well, F prime is proportional to mass x times mass y over r squared. Mass x did not change, so that stays 1. Mass y doubled, so that's a 2, divided by the distance that did not change squared, which is 1 squared. Again, 1 times 2 is 2 over 1 squared is 1, gives us 2. And the new force is, again, double when we double one of the masses. Now, what if both x and y are both doubled? So mass of x times mass of y divided by r squared. So if mass x doubles, we replace that with a 2. Mass y also doubles, we replace that with a 2, divided by the distance, which did not double, or did not change at all, so I replace that r with a 1 squared, and I get 4 over 1, which is 4. What does that mean? It means the new force is 4 times greater than the other force. The gravitational force has quadrupled. Okay, so relative analysis simply means if a variable changes in a certain way, doubles, triples, cuts in half, then how is the other variable that is dependent on that changing variable, how does it change proportionally? That's what proportional reasoning looks like. Okay, so again, this is a proportional reasoning approach. Which involves how does something change when a variable changes. It's not an absolute calculation. At this time, go ahead and take a second, pause the video, and try the last 3 examples yourself and see if they match with what I go over. Give it a try right now. Okay, let's see how you did. In the 4th example, the distance between them is doubling. So f prime is proportional to mx times my over r squared. Neither mass changes, so I replace both of them with a 1, but this time the distance is doubled, so I'm going to replace r with the number 2 and then square it. So 1 divided by 2 squared is 1 divided by 4. That means the new force is 1/4 the original force, or the force has decreased by a factor of 4, would be another way to state it in words. The distance between is now 1/3 as much. Force is proportional to mass x times mass y divided by r squared. Again, neither mass changes, so we replace both those with a 1, but the distance is now 1/3 as much. So I'm going to put 1/3 in place of r, and then I'm going to square that. That would be 1 times 1 is 1, over 1/3 squared would be 1/9. Now, if I'm dividing by 1/9, ladies and gentlemen, that is the same as multiplying by 9, which means making the distance closer by 1/3 as much means the force is now 9 times greater. That should make sense. Something closer is going to have a stronger gravitational pull than something farther. So moving the distance 1/3 as close means the gravitational force is 9 times stronger. And in this last example, we have a mass doubling, both masses doubling, and the distance between them tripling. F prime is proportional to mass x times mass y over r squared. So we have double times double, both masses double, divided by the distance between them, which is tripled squared. 2 times 2 is 4, over 3 squared is 9. It means the new force is 4/9 as big. Now, 4/9, what is 4/9? Well, 4/8 would be a half. So 4/9 would be a little less than a half. So the new force is basically a little less than half the old force. That's kind of another way to think about it. What is the equation for the acceleration of gravity, little g, in terms of the gravity constant, big G, the mass of the planet, big M, and the radius of the planet, big R? Well, the equation we get is very similar to the gravitational force equation, big G, M1, M2 over R squared. But instead of M1 and M2, let's say we just call it, big M and little m for mass of the planet and mass of a satellite orbiting a planet. Okay, divided by r squared. So the equation for the acceleration due to gravity, little g, is big G, big M over r squared, where big G is the acceleration due to gravity, which on Earth you know to be 9.8 meters per second squared at the surface of the Earth in meters per second squared. Big G is the gravity constant. The gravity constant is still a value of about 6.67 times 10 to the negative 11. Big M is the mass of the planet, or mass of the moon, or mass of the comet, mass of whatever, mass of a star, mass of some celestial body in kilograms. And R is the radius of that planet. Think of it this way. It's the distance between the surface of that object and the center of that object. Also in meters. Show how this equation is derived using the two equations for force of gravity. So this is how we derive it. We know that the gravitational force on the surface of the Earth is m times g. But we know that universal gravitation between any two masses is big G times little m times big M divided by r squared, where big M is going to be planet and little m is object at the surface of the planet. And r is, of course, the distance between those two, which would essentially be the radius of the planet, since any object at the surface is essentially a radial distance away from the center. Now, since both of these are equal to the gravitational force, we set those equal to each other. And so mg, little mg, is equal to big G, little m, big M over r squared. And you can all see that the little m's, the small mass at the surface of the planet, would cancel, and we are left with little g is equal to big G, big M over r squared, which is what we had written above. So that begs the question, what should we use mg for in terms of gravity force? Well, if you heard me mention it a few minutes ago, mg is used when we're talking about near the surface of the Earth, or whichever planet we're talking about. Test your understanding. What would happen to Earth's gravity if Earth was twice the radius but had the same density? Explain all of your thinking. Well, we're going to explain this mathematically using proportional reasoning, and then we'll put it all together and sum it up in words. Okay, so the first thing I would tell you is that when we're dealing with density, density is the variable rho. Kind of looks like an italicized p. And density is the mass of an object per unit volume. So it's the mass divided by the volume. If we solve for mass, means we multiply both sides by volume, and the mass of an object is its density times its volume, which means however the volume changes, the mass changes. They're directly related. So for instance, if the volume doubles, the mass doubles. If the volume cuts in half, the mass cuts in half. That would be assuming the density stays the same. If the density changes and the volume changes, then the mass is going to change accordingly. So one thing to think about in terms of a planet is essentially a spherical object, and the volume of a sphere is 4/3 times pi times r cubed. What this means is volume is proportional to radius cubed. So let's look at what we have here. Earth has twice the radius, but the same density. So twice radius, same density would mean that the mass is going to be the same density, so we're going to place density with the number 1 because it doesn't change. But the radius, what happened to the radius? See, if the radius doubles and volume is proportional to radius cubed, that means if we double the radius and we cube that, 2 cubed is 8. So the volume, if we double the radius, the volume actually increases by 8 times more, which means the mass is 8 times more. So the new mass is 8 times the original mass. So if we were to double Earth's radius, the volume octuples, right? Fancy word for 8 times greater. And the mass also is 8 times greater. So now we throw that into, it's asking what would happen with Earth's gravity. Well, we know that Earth's gravity is proportional to, we know if the equation is equal to big G, big M over R squared, but we could write it as a proportionality of big G, of simply big M over R squared, and forget about big G. So what does this mean? The mass is 8 times bigger, and the radius is double. It should be 2 squared. So 8 over 2 squared would be 8 over 4, or 2. What does this mean? Earth's gravity would be double. What does Kepler's first law say? Well, Johannes Kepler was a scientist who lived after the age of Newton, and he did a lot of astronomical work to view specifically decades worth of data on Mars as it traveled through the sky. This was using a kind of one of the earlier telescopes. And in his first law describes all objects, all planets, essentially orbit the sun as ellipses. Ellipses are elongated circles, kind of like what we see over on the side right here, where instead of having just a circle, you have what are called foci, or focus points. So one focus point, and then you have another focus point on the other side. Well, the sun is one of those focus points right there. We call it foci for plural. Focus singular, foci plural. The second law states that a line joining the planet to the sun is going to sweep out equal areas in equal time intervals. So if we drew a line from here to here, and the planet, let's say, is right here, and we follow that to this point right here, and let's say that's swept out a 10-day interval right there. Let's say that was 10 days. Then that means that this area from here to here, if that's the same 10-day time interval, that area is the same as that area right there. Okay, now the picture is not drawn to scale to represent that, so I think a better picture of this would be like this area right here, and that area right there, and that area right there. So those shaded areas would be the same if that time interval from here to here, from here to here, and from here to here is all the same. So equal times sweep out equal areas. Write Kepler's third law, known as the square-cube law, in a short sentence and as a ratio equation. Well, all objects orbiting the same central body have the same ratio of t squared to r cubed. So what Kepler's third law states is that the square of the period is proportional to the cube of the radius. And we're going to derive this right now. How do we derive Kepler's third law? Well, you derive Kepler's third law by first starting with the following sentence. Gravity is a centripetal force. We talked about centripetal forces as forces that cause circular motion. Gravity, that would be big G, big M, little m over r squared, equals centripetal force. The equation for that was mv squared over r. So there's our equation. Now we're going to also need the following equation for the speed of the object. Remember the equation, the speed of an object is equal to the circumference, 2 pi r divided by the period t? Well, we're going to be substituting in a minute for v squared, so let's square everything here. If v is 2 pi r over t, so v squared would be, well, square 2 and we get 4. Square pi, we get pi squared. Square r, we get r squared, and square t, we get t squared. So 4 pi squared over t squared would be v squared if we squared everything. Notice the masses cancel, and one of the radii factors cancels as well. And you're left with big G m over r equals v squared. Now, you want to substitute that for that. And we get big G, big M, little r equals 4 pi squared r squared over t squared. Now, at this time, let's bring some of the r's together. I'm going to do that by multiplying both sides by r. Okay, and then I'm also going to swap t squared and gm. And as I do that, I get t squared as my dependent variable equals 4 pi squared. R squared times r would be r cubed over, and then g times m moves down here. G m. And if you look at what we're left with, t squared is proportional to r cubed, because all of that is a constant. 4 pi, g, and m are all constants. Now, you could write this one more way, and that is to divide the r cubed both sides, like this. And we get t squared over r cubed equals 4 pi squared over gm. And that, ladies and gentlemen, is a constant value, which will end up being the slope when you plot t squared as the rise versus r cubed, which is the run. So if you plot that planetary data, you'll get a constant slope, and that slope will be equal to this ratio here of 4 pi squared over g times the mass of the planet. So this is Kepler's third law written in equation form. This is the law written as a proportion. And if we want to write this as a way of kind of comparing two orbiting bodies, we would just simply write it like this, where we say all orbiting bodies have the same, if you have two orbiting bodies that orbit the same central body, they all have the same ratio of t squared over r. I miswrote that, I'm sorry, that's r cubed, not r squared. Okay, and so what we would say is t squared over r cubed is equal to t squared over r cubed. And so t1 squared over r1 cubed equals t2 squared over r2 cubed, where 1 and 2 are two bodies. So for instance, if you have two objects like Earth and Saturn, which both orbit the sun, 1 would be Earth, 2 would be Saturn. Let's take a look at a couple examples to finish this up. Test your understanding. Suppose you know that the moon orbits the Earth at a radius of 3.84 times 10 to the 8 meters and takes 27.3 days to go around the Earth. A geosynchronous satellite takes 1 day to go around the Earth. What is the radius of the geosynchronous satellite's orbit? Okay, so there's the equation we're going to work with because we have two bodies that are orbiting the Earth. You know the moon orbits the Earth and this satellite orbits the Earth. So t squared over r cubed equals t squared over r cubed. But we're talking about the moon and a satellite. So tm over rm, ts over rs, where m stands for the moon and s stands for satellite because both of them orbit the Earth. Now, you're solving for the radius of the satellite, so you're solving for rs. Now, I think what I would do to solve this equation is I would first take the cross products of these and then divide away the unknown, or divide away the other information. So if I multiply across, I get tm squared times rs cubed equals ts squared times rm cubed. Go ahead and divide away the tm squared so you can solve for the radius of the satellite. And what we have here is we have rs is the cube root. We'll talk about how to take the cube root in a calculator in a minute. Cube root of what? Well, ts squared is the satellite. Now it takes The satellite takes 1 day, because geosynchronous means the object, the satellite orbits at the same rotational rate as Earth's orbit. So Earth takes 1 day to spin around. So if the satellite is going to be the same spot around the top of the Earth, say it's a communications satellite directly over San Diego, California, then it needs to rotate along with Earth for that satellite to stay above San Diego, California forever. So TS would be 1 squared, 1 day squared. The radius of the moon would be the 3.84 times 10 to the 8, but you need to remember to cube that, divided by TM squared. Well, that would be the period of the moon. Takes 27.3 days, takes almost 1 complete month, 27.3 days. And we need to remember to square that data. Okay, so when you put all of this in the calculator, you're going to get a pretty big number. In order to take the cube root of that, here's what you do. To take a cube root of a number, all you do is you raise that number to the 1/3 power, because raising something to the 1/3 power is the same as a cube root. Okay, so that's how you can do that in your calculator. Take a second and pause the video and try and see if you can get the radius of this particular satellite. Okay, you should have gotten somewhere in the neighborhood of about 4.2 times 10 to the 7 meters, which is the same thing as 42 times 10 to the 6 meters, or 42 million meters. Test your understanding. Earth's distance from the sun is defined as 1 astronomical unit, and the Earth takes 1 year to go around the sun. If Saturn is 9 astronomical units from the sun, how long does it take Saturn to go around the sun in terms of an Earth year? Well, you know it's farther out, so you know it's going to take more than an Earth year. Well, how many years does it take? Well, let's start off with the equation. T squared over r cubed equals T squared over r cubed. Now, Earth would be one variable, and Saturn would be the other. And you're solving for the period of Saturn. So, again, we could take the cross products and then divide away the unwanted quantities. So, TS squared times RE cubed equals TE squared times RS cubed. Divide away the RE cubed. And the period would be the square root, because I have to square root to get rid of the square. It's going to be the square root of the period of Earth. The period of Earth would be 1 year. It takes 1 year to go round. The radius of Saturn is 9 astronomical units, and I have to cube that. So 1 year squared divided by 9 cubed, so I got to cube the radius, over Earth radius. Now, Earth's would be 1 astronomical unit, and I have to cube that as well. So essentially, what are we doing? We're taking 9 cubed, and then we're going to square root that. Take a second to put that in your calculator and see how long it takes Saturn to orbit the sun. If you put that in your calculator correctly, you should have come out with 27 Earth years. It takes 27 Earth years for Saturn to make its way once around the sun. Kind of a long time. Test your understanding. Suppose you have the data for the period T of the orbit of 5 of Jupiter's moons. You also know the radius of each of the moon's orbits. What data would you need to plot in order to get a straight line for this data, and what would the slope be? Well, we talked about this a few moments ago. Remember the idea that T squared over R cubed is constant, and that constant value was 4 pi squared over GM. And that constant value is going to be the slope when you plot t squared as your rise over r cubed, which is your run. So your horizontal variable would be your run, that would be r cubed, and the units would be meters cubed, over the vertical variable, which is t squared, which would be seconds squared. The slope would be your 4 pi squared over gm, where what you'd be looking for in this case is usually the mass of the planet being orbited or the mass of Jupiter. Section 4.6. Satellites and astronauts. What does the term geosynchronous or geostationary mean? What is the period in seconds of a geosynchronous orbit? Okay, so we talked about this a few moments ago. Geosynchronous refers to rotating at the rate of Earth's rotation, which is 24 hours. Now, if you take a second to convert that, 24 hours times the fact that every hour is 3,600 seconds is 86,400 seconds for one revolution of the Earth. That means a satellite in a geosynchronous orbit takes 86,400 seconds to make one full rotation around Earth. What is the basic procedure for solving any problem dealing with a circular orbit? Find an example on page 182, write an equation 2. Well, the equation is basically treat gravity as a centripetal force, like we did to derive Kepler's third law. Big G, big M, little m over r squared equals little m of the satellite times v squared over r. And you typically also have to use the fact that the velocity in orbit is 2 pi r over the period t, combining those together. Usually it ends up being Kepler's third law. Okay, test your understanding. Determine the radius of orbit and the speed of a geosynchronous satellite. Use the mass of Earth as 5.98 times 10 to the 24 kilograms, and big G is 6.67 times 10 to the negative 11, and a calculator. Well, we established earlier that if we talk about gravity being a centripetal force, and the fact that V is 2 pi r over t, or rather v squared is equal to 4 pi squared r squared over t squared, then big G, big M over r is equal to 4 pi squared r squared over t squared. And when you combine those r's together, we did this a few moments ago, we get t squared equals big G M, or excuse me, equals 4 pi squared r cubed over G times big M. Okay, now what we're doing is we are not comparing two different objects. We're looking for one particular variable from one particular object orbiting the Earth, not two different objects. So we're not going to use the proportion of t over r equals t over r. We're just simply going to use Kepler's third law. But we're going to solve for radius. So to solve for the radius, we're going to multiply by gm, divide by 4 pi squared, and then we're going to cube root that radius. So the radius is going to be the cube root of g times m times the period squared over 4 times pi squared. So you have 6.67 times 10 to the negative 11 times mass of the planet, which is 5.98 times 10 to the 24 kilograms, times the period. The period, well, here's the thing. What would the period be? The period's 1 day. And we already established in the previous example, 1 day is 86,400 seconds. But you got to square that because it's the period squared. So we got to square all that. Divided by 4 pi squared. Now, the easiest way, I think, to put this in a calculator would be multiply all that. First of all, square that number, times this, and then write that number down up here. Then go ahead and go 4 times pi squared and write that number down here. Then divide those two and raise it to the 1/3 power, and you will have cube rooted that answer. Everybody take a moment and try and put this in your calculator and see if you can get the radius of that geosynchronous orbit. Okay, doing this correctly, you should have gotten about 1.94 times 10 to the 8 meters. Explain why objects in orbit appear weightless. Well, objects in orbit appear weightless because gravity makes things fall towards the Earth. But if something is in orbit, it's also flying forward at the same time. So you could think of something that is appearing weightless is really in a perpetual or constant state of free fall. Thus, if you were to stand on a scale, the scale would read 0. It's not that there's zero gravity. There's still gravity up in space, but since you're falling towards the Earth and flying forward at the same time, you're going to be continuously falling forever towards the Earth. Hence, weightless. Let's take a look at this last example. We have an accelerometer is placed in a car. The accelerometer measures the acceleration of the car in the car's reference frame along the two axes X and Y as shown. You can see that in the picture of the car right here. The X acceleration is plotted as black dots and the Y acceleration is plotted as white dots. In the parking lot, draw a motion map representing the car's motion, assuming the car is initially at rest and pointing north. So a motion map means we're going to use arrows to draw, constant speed, elongated arrows to show increasing velocity, shorter arrows to show slowing down, curving, etc. So again, let's break this down. Acceleration in the X, black dots, acceleration in the Y, white dots. So acceleration in the X direction, black dots, and ladies and gentlemen, the black dots would be showing you the direction of curvature. This is possible centripetal acceleration. What that means is you're curving. You're curving in a circle. Acceleration in the Y direction, those we were told are the white dots. And if you look in the Y direction, that's to the front and rear of the car. So that means possible tangential acceleration. Tangential acceleration means acceleration in the direction of motion, which means we're talking about speeding or slowing. So let's take a look at one direction at a time. Okay, let's focus on the white dots first. Now, according to this, it appears that from 0 to about 2 seconds, you're going at no acceleration, so we're going at a constant speed forward. And then it appears that from 3 to 5 seconds, this part right here, we accelerate, meaning we are speeding up. You're speeding up. But notice your acceleration in the X direction is still 0, so you're not curving. You're just simply speeding up going forward. Okay, then what happens to the white dots? The white dots come back towards the middle, which means we go at a constant velocity from 5 to, it looks like 12 seconds. Then the white dots for 2 seconds, the white dots appear to be slowing down. You appear, because you have negative acceleration, and negative acceleration would be in the negative Y direction. So we are slowing down from about, 13 to 15 seconds? And then the white dots are showing you 0 acceleration, so constant velocity all the way. So that's what's happening with the white dots. Let's look at the black dots. The black dots are showing you constant velocity for about 7 seconds. It's showing you acceleration in the negative direction, the negative x direction, so it means we're going to be curving, because negative x direction is to the left, we're going to be curving left. And then we're going to immediately be changing direction to curve right. Something I want you to notice about each curve. The acceleration in the y direction is 0, so you're not speeding up or slowing down. You're going at a constant speed as you make the curve. So this is uniform circular motion. It's curving in a circle, centripetal acceleration, with no increase or decrease in speed as you do it. So first we curve left, then we curve right. Then you notice the black dots come back down to 0 for constant velocity in the x direction, meaning we go in a straight line for part of this, but we're slowing down as we do so. So what would this look like if we map this? Well, first, let's go ahead and draw constant speed for a little bit. So we're going to go a couple arrows, same length. Then all of a sudden, we're speeding up, so we're going to draw the arrows longer, like this. And I probably shouldn't draw so many arrows there. So let me draw this. Because I'm going to run out of room if I do. So we've got constant speed for a little bit right there. And then all of a sudden we have a big jump in speed. There's the velocity. Okay. Now all of a sudden we curve left, maintaining that same speed. So curve left, maintaining that same speed. Then immediately we're going to curve right, which means maintaining that same speed, we're going to curve right. And again, I'm kind of running out of space here, so I'm going to make this picture a little bit smaller. Okay. And then notice we're going to do what? We're going to now slow down for the rest of the journey. So the arrows are now going to get shorter again, and they're going to be ending up with constant velocity. So our motion map might look something like this. Constant velocity, speed up, curve left at a constant speed, curve right, slow down, because you're going from a longer velocity, a faster velocity to a slower velocity, so slow down. And then constant velocity the rest of the way. I hope you found this video helpful. Please remember to rewind or pause the video as necessary, and please remember to ask any relevant questions that you have pertaining to any concepts that we've gone over that you still don't understand. Thank you.